Look closely at a chemical reaction in a fluid. It is a turbulent environment. Swarms of atoms rapidly collide, violently exchanging their outermost electrons. These spontaneous chemical reactions naturally release energy. But when you mix the reactants directly in a single container, that energy has nowhere to go. It is entirely lost to the surrounding environment as ambient heat. Electrochemistry offers a mechanical solution to this problem. By engineering a physical barrier between the reacting chemicals, we can intercept those transferring electrons and force them to perform measurable electrical work instead of just generating heat. This is how early scientists constructed those physical barriers. By isolating the reactive elements into separate metallic and ceramic components, they built the first solid-state engines capable of harnessing chemical potential. The process also works in reverse. By applying external electrical energy, we can force otherwise non-spontaneous chemical reactions to occur, driving elements apart against their natural thermodynamic tendencies. The electrochemical cell is the bridge between chemical thermodynamics and electrical engineering, mediating the transmission of sensory signals in the brain and the industrial synthesis of metals. To see how this architecture works, we examine a standard redox reaction. This diagram shows a solid zinc rod dropped directly into a blue copper sulfate solution. At the atomic level, zinc atoms naturally dissolve into the fluid as positively charged ions. As they do, the copper ions in the fluid pull electrons directly from the zinc, depositing onto the rod as solid metal. Because this electron transfer happens locally, right at the metal-liquid boundary, the energy is trapped. No electrons travel through any external circuit, meaning this violent reaction produces absolutely zero electrical current. To capture electrical work, we must physically quarantine the chemical losing electrons from the chemical gaining them. We take the components of our single beaker and separate them into two distinct environments, connecting them with an overhead metallic wire to form a galvanic cell. Zinc possesses a lower standard reduction potential, negative 0.76 volts, compared to copper's positive 0.34 volts. This means zinc has a greater thermodynamic tendency to lose electrons. We define this zinc electrode as the anode. Here, the metal undergoes oxidation by losing electrons, which are forced up into the connecting wire. The electrons travel through the circuit and arrive at the copper electrode, the cathode. These arriving electrons facilitate the reduction of copper ions, pulling them out of the liquid to form solid deposits. Because of this continuous transfer, the physical mass of the electrodes changes. The zinc rod actively shrinks as its atoms dissolve into the fluid, while the copper rod grows thicker as new metal accumulates. There is a quirk in how we measure this flow. While physical electrons move from the anode to the cathode, standard electrical current is conventionally recorded moving in the exact opposite direction. By separating the reactants and routing the electrons through a wire, we have successfully converted chemical potential into a directional electrical current. Despite our separation, this setup has a fatal flaw. If you build this exact circuit, the current rapidly slows down and dies within seconds. As the zinc oxidizes, the left beaker becomes choked with an overwhelming excess of positive zinc ions. Simultaneously, as positive copper is removed from the right beaker, the leftover sulfate ions create an overwhelmingly negative environment. This localized ionic charge buildup creates massive electrostatic repulsion. The positive charge on the left pulls back on departing electrons, and the negative charge on the right repels incoming ones, actively blocking any further current. Sustaining a directional current depends on maintaining chemical neutrality in both half cells. To solve the electrostatic crisis, we install a U-shaped tube spanning the two half cells. This is the salt bridge. It contains an inert electrolyte solution designed to actively counteract the charge buildup without interfering with the main reaction. As the cell runs, negative ions from the bridge pour into the anodic beaker to neutralize the positive zinc buildup, while positive ions pour into the cathodic beaker. They rapidly neutralize the liquids. This allows the system to balance its internal charge without letting the two distinct chemical solutions directly mix. By maintaining internal charge balance, the salt bridge completes the circuit and allows a continuous electromotive force to drive electrons through the wire. We represent this complex physical system using a universal shorthand known as standard cell notation. The grammar is precise. The single vertical lines represent phase boundaries, where the solid metal meets the liquid electrolyte. The double vertical line in the center represents the salt bridge dividing the two half cells. The pressure driving electrons through this system is called the electromotive force, or EMF. It is the quantitative potential difference between the right half cell and the left half cell. We calculate this using standard reduction potentials. The total cell potential equals the potential of the cathode minus the potential of the anode. Substituting our specific values for copper and zinc gives us positive 0.34 volts minus negative 0.76 volts, resulting in exactly 1.10 volts. That 1.10 volts is the absolute thermodynamic ceiling for the spontaneous energy produced by this specific chemical pairing under standard conditions. What happens to this carefully balanced 1.10 volt system if we deliberately attack it with an opposing external electrical voltage? If we apply an external voltage but keep it below 1.10 volts, the galvanic cell continues to function spontaneously. The electrons simply operate against the new electrical resistance, moving sluggishly from zinc to copper. When we increase the external voltage to exactly match 1.10 volts, this opposing force creates perfect equilibrium in the circuit. At this exact threshold, the chemical reaction stops entirely. Zero current flows through the system. But when the external voltage exceeds 1.10 volts, the external electrical force overpowers the thermodynamic drive of the chemicals. The entire system reverses, forcing electrons backward from copper to zinc. Exceeding the EMF threshold strips the system of its spontaneity. It turns a power generator into a power consumer. This reversed system is formally known as an electrolytic cell. Its core trait is transforming external electrical energy into chemical energy to drive non-spontaneous reactions. In this state, the physical roles are inverted. The electrode that was losing electrons is now gaining them, completely swapping the polarities of the anode and cathode. This exact interconversion principle is what allows modern lithium-ion batteries to function. They alternate seamlessly between discharging power spontaneously as a galvanic cell and recharging on a wall outlet as an electrolytic cell. We apply this same mechanism at an industrial scale. By forcing non-spontaneous reactions in massive electrolytic tanks, we can harvest raw chemicals and purify metals directly from their ores. Electrochemistry governs the industrial production of chemicals and the development of energy-efficient technologies, providing the mechanism to control chemical energy through electrical command.